So my name's Neil Madden, and this is a talk about practical cryptography with Google's Tink library. So there's lots of tutorials and things online where you can find out the theory of cryptography, but there's relatively little about how to actually translate that into working code and avoiding some of the security vulnerabilities that can arise. And so this talk is partly about modern cryptography and what you should be implementing and how to implement it securely. But it's also a little bit of a look at Tink and some of the lessons we can learn from Tink about secure library design and how you can design libraries and frameworks for developers to use that kind of avoid some of the sharp edges around security tools and avoid some of the security issues that might arise. Before I go on, by the way, the organisers asked me to say when you leave at the end of here, there's buckets with red, green and yellow things, depending on whether you like the talk or not. So the green ones, if you like the talk. If you didn't like the talk, that's also the green ones, apparently. So moving on. So a little bit about me and why you might want to listen to me for the next hour or so. So I'm the author of API Security Action. I've done a bit of security research, found a critical vulnerability in Java's signatures a few years ago. I'm also a long-time contributor to the OAuth and Jose working groups at the IETF and do a bunch of things. That is not a phishing awareness test, that is my blog, if you want to look that up. So Tink then is a high-level cryptographic library that's developed by Google. And as I said, it's designed to avoid a lot of the kind of security vulnerabilities that can crop up when you're implementing cryptography in your applications. It supports a bunch of different languages, so primarily kind of server-side languages, but they also support mobile development through Objective-C, and the Java runs on Android as well, so they support the mobile app. So we'll see a little bit later about some of the features around that. It's been developed by some very well-known cryptographers and cryptographic engineers who were at Google at the time. So Yong Tai is responsible for various attacks on SSL, so the crime, beast and poodle attacks, which are very famous attacks on SSL. He was co-responsible for those, and Daniel Bleikenbacher gives his name to some very famous attacks against RSA encryption. So this is a kind of appeal to authority that the people who built Tink really knew their stuff when it came to cryptography. And so it's been designed to be easy to use securely, and more importantly, to be hard to use insecurely, which is kind of one of the major themes in this. All right, so let's get on and look at some example code. So this is a security conference, so hopefully most of you will have a basic idea about cryptography. But for those that don't, this is just a brief recap. So the kind of gold standard of encryption that you should be using in 2025 is what's called authenticated encryption. So in this case, we're talking about symmetric encryption. So Alice and Bob both have a shared secret key that they use, and they can both encrypt and decrypt. We'll talk later about public key encryption and things like that as well. And so old style in the early, the 90s and early 2000s, cryptographic modes just basically concentrated on confidentiality. So it was about just encrypting some data to keep it secret. And we've since learned that you need a lot more than that really to have secure encryption. So if you just focus, so some of those old confidentiality only modes, you can't read the data if you don't have the key, but you might be able to tamper with it in ways that cause predictable effects on what it decrypts to. So you can tamper with the ciphertext, as we call it, and then that will cause corresponding changes in the plaintext. So the classic example is Alice is sending a message to a bank saying something like, pay Bob $1,000, and Eve can intercept it and flip some bits in the ciphertext. She doesn't know what it says, but she can maybe guess on the format. And now when the bank gets it, it decrypts and it says, pay Eve $1,000 instead, right? So now we kind of believe that you need to have this level of data integrity as well as confidentiality. And in fact, if you don't have that integrity, then you often lose confidentiality as well, because when you decrypt data that's been tampered with, it often fails to decrypt, or your application fails to process it afterwards in ways that leak information about what the rest of the message contained. And so authenticated encryption also provides a stronger property, which is called data origin authentication, or also message authentication, where you get some guarantee about where the messages come from somebody that you trust, somebody who has access to this secret key. So as it's a security conference, we're often talking about threat modeling. Lots of you may have used STRIDE threat modeling. So in terms of STRIDE, this is protecting against spoofing, tampering, and information disclosure. So you've got 3 of your STRIDEs kind of sorted at once. So that's really what you should be using in the modern day. All right, so we're going to have a look now at some horrible code. This is old-fashioned code from the Java Cryptography API for doing authenticated encryption. I'm going to use the laser pointer. I'm going to have to pick one thing. There's no cats in the audience, I hope. So one of the things is that we just got this generic cipher abstraction here. And I happen to know that this AES GCM, which is Galois counter mode, is an authenticated encryption mode. But this cipher class also does unauthenticated encryption. It does the old style encryption. It does absolute garbage encryption schemes like ECB, which don't really provide you any security at all. And it also does like public key encryption as well, and things which have like wildly different security properties. So a lot of the security comes immediately from knowing what to put in this string at the start. I think Thomas Tatchek, famous security researcher, once said, if you're typing the letters AES into your code, you're doing crypto wrong. And there's other little details here, like this IV. So every time you encrypt something, you have to provide a unique or random initialization vector, sometimes called a nonce, for number used once. And one of the things that Java does right is it will actually generate that for you, but you still have to worry about it, and you still have to kind of, this is like a 16-byte or something thing that you have to kind of get back from the cipher, and you have to remember to write it out with the rest of your stuff. Otherwise, you won't be able to decrypt it later on. And there's a whole bunch of other things in here that you have to remember. Decryption, similar, right? There's a whole bunch of things I have to know. I have to know that for GCM, in fact, that nonce was 12 bytes. It's normally 16 for AES, but for GCM, it's 12 bytes. So I either have to know that, or I have to encode it into my output stream and stuff. So there's just all these details I have to know about. There's this GCM parameter spec, which is totally specific to this. So you've got this generic API with the string here, but then I have to provide this totally specific class down here. So there's all these kind of details, basically. There's a whole bunch of gotchas here. So this is that same decryption code, but the decryption and the encryption are kind of similar code. So typically what a developer will do will write the encryption part and then copy and paste it into the decryption thing and then make the changes until it works. But if they accidentally leave that saying encrypt mode, does anyone know with GCM what would happen if you try and decrypt but you've got it in encrypt mode at all? Does anyone know? Anyone want to hazard a guess? It works. So encryption and decryption in GCM are the same operation. And so it will decrypt, but what it won't do is verify the authenticity of the data. So you would just silently not be authenticating the data. You might get, depending on which method you call, you might get some random garbage stuck on the end of the message, but often applications will tolerate random garbage on the end of messages. So there's little gotchas there. There's another gotcha here. So what's this magic number here? That's 128. In fact, that number should never be anything other than 128. Otherwise, you've probably got a security vulnerability. So down here, this is like the Mars orbiter that crashed famously because of a mismatch between imperial and metric measurements that meant it was approaching Mars too quickly and crashed into the surface. So there's a similar thing here. A really classic blunder in crypto is having confusing bits and bytes. So that parameter there is 128 bits, and it's the length of the authentication tag. If you mistake that for bytes and put in 16 there, you'll get a 16-bit authentication tag, which can be instantly brute forced. So this happened, so Bouncy Castle had a bug with this. It's happened in loads of different crypto libraries. So Bouncy Castle had a bug where they mixed up bits and bytes in an interface and generated 16-bit keys for encryption. Right, again, trivially brute forced. But yeah, that is the only value that makes any sense in this thing, but it makes you specify it. So these old-style crypto libraries are characterized by having lots of very general abstractions, loads of different choices for algorithms and things, and that you as a developer assumed that you know what you're doing and that you're an expert and you can navigate these incredibly subtle security choices. And so they're very easy to misuse because of that. And it's not just Java as well. This was a nice one. So Adam Shostak tweeted this last night, and I added it last night. So there's a nice blog post where somebody has mocked up what OpenSSL would look like if it was a user interface. And it's just like tabs and tabs and pages of checkboxes and things like that. And nobody could possibly understand this. Like, you would never tolerate that as a UI. So why do we tolerate this as a developer API for our libraries? So modern crypto libraries are designed to kind of avoid all of these pitfalls and these little subtle security vulnerabilities. So Tink is one of these. Probably the first one was what's either called NaCl. I think everyone calls it NaCl that I know of, but it's supposed to be salt because NaCl, sodium chloride, right? It was the network and cryptography library, although there's no network code in the library at all. And so NaCl was developed by Daniel Bernstein, who's a very well-known cryptographer and security engineer. And it takes a very opinionated view of cryptography. So you just have functions effectively which say, like, encrypt this. So you give it some data and you give it a key and it encrypts it. And you don't get to say what algorithm to use or any of the parameters or anything like that. Dan Bernstein, who is an expert, has chosen those algorithms and parameters for you. And you use the Dan Bernstein approved crypto suite, which is great. And they all are very highly secure algorithms, and they've stood the test of time. But as developers, often you're not in the luxury position of just being able to just say, oh, I just want to do encryption and I don't care what algorithm it uses. Normally, you've got to interoperate with some other system, or you've got to implement a spec or something like that, where the algorithm is specified for you, and that's what you need. And so if NaCl doesn't implement that algorithm, then you have to go back to using some low-level library. So Tink kind of sits in the middle of those, where it provides a high-level hard-to-misuse library, but it also gives you some flexibility to choose the algorithms and choose some of those parameters, but in a way that's done safely. All right, so this is how you encrypt a file in Tink. So we haven't got a general cipher. We've got this thing called an AEAD, which is a bit of a mouthful, but that is Authenticated Encryption with Associated Data, and it's a kind of standard acronym used in cryptography. So whatever I get back here that satisfies this AEAD interface, I know it's Authenticated Encryption. So whenever I see this class being used in some Java code, I know from my stride thing that I'm preventing spoofing, tampering, and information disclosure. Right, I know that it's got that. Whereas if I see a cipher being used in some Java code, I have absolutely no clue what security properties it satisfies. And then really the encryption then just becomes a one-liner, right? There's no initialization, there's no messing around with IVs or anything like that. You just say, encrypt this stuff, and here's my associated data. Associated data you don't really need to worry about. It's just some extra context that you want to be authenticated but not encrypted. So in this case, we're sticking the file name in to prevent somebody copying and pasting encrypted code to a different file. And so you just encrypt, you get back the encrypted ciphertext, and then you write that out to your file. And it's taken care of the IV, it's prepended the IV onto here, and it's generated it all for you securely, so there's nothing you need to do about that. Likewise, decrypting again, same thing. So we use this key set. I'll talk later about what key sets are, by the way. We get back this AEAD, and then we just decrypt again. Again, passing the same file name, otherwise it won't decrypt. And that's it. It doesn't have any of the same security pitfalls that we had in the plain Java code. Even if you copied and pasted this, because again, this looks pretty similar, and left that as encrypt, it wouldn't work. What you would get back is totally random. It would re-encrypt it with a new random IV. So it would not decrypt, and what you'd get back is some garbage. So your application would go and process that, and it would fail, But because what it's getting back is totally random, it's not going to leak any information about what was in the rest of the message, because no part of it has been decrypted. So some of the kind of design principles of Tink then is that each cryptographic primitive has its own interface, so it's well typed in each language. So when you see a particular interface like AEAD, you know that every single implementation of that interface satisfies the security goals. And if you go and look at the documentation for Tink, they have like quite detailed security requirements for the things. So it talks about, you know, how many messages you can encrypt before you start losing these things and so on. So there's kind of baselines of that kind of stuff. And so you can choose your algorithm depending on the other kind of quality attributes you want to achieve in your code, like performance or, you know, scalability or whatever else, but you know you're getting this baseline security. Okay, so the downside of that code that I just showed you is that it was a single-shot API. All of your data had to be in memory at once for you to be able to encrypt it or decrypt it, which is fine for short bits of data. Lots of stuff that applications do are exactly like that. They're small bits of data, a few kilobytes or megabytes. But if you've got larger data that you need to encrypt, then you really want to do streaming encryption. And again, the old style Java API has this cipher input stream and cipher output stream that you can use to wrap an input and output stream, and it will do encryption and decryption on the fly. And it's generally a good idea, but one really serious problem with this API was it was designed and added to Java before authenticated encryption was conceived of as a thing that we needed to do. So this, I believe it was added in Java 1.4, which is 2002. And the first authenticated encryption modes didn't come out until a couple of years after that. And so it has no way of signaling that authentication failed. All it can do is throw this generic IO exception. So it gets to the end of the stream, tries to authenticate the data, goes, okay, right, that failed, so I'm going to throw this IO exception. And this is pretty much, if you look in any Java code base anywhere and look at how people handle IO exceptions, almost without exception, they just log it and move on because nobody really knows how to handle IO exceptions. And so you've already processed all the data then, and you find out that somebody's tampered with the data, but maybe you've got a log message that you can see after the fact. And another problem then as well is like when does it actually verify that authentication tag? It does it right at the end. The way authenticated encryption works is you encrypt the data and you write it out, and then right at the very end there'll be like a 16-byte authentication tag that gets verified. And so if we're processing like gigabytes of data or something like that, and we're streaming it through, it's only when we get to the very end that we're going to find out that anything's been tampered with, which is too late by that point, because we've already been reading in chunks of data and processing them, unless you're going to buffer it all up in memory again, or have some massive transaction that you're going to roll back at the end, neither of which kind of defeat the purpose of what you were doing in the first place. And so we call this generally releasing unverified plaintext, the idea that you're processing data that you've decrypted before you know whether it's authentic or not. And so Tink provides what it calls a streaming AEAD, so that's again authenticated encryption, which is a kind of drop-in replacement for these old Java classes. But again, there's a specific interface here, and then we can wrap our input and output streams. And what this does is it chunks up your data for you. So in either, I believe it's 8 kilobytes or 1 megabyte chunks. And it encrypts and authenticates each chunk individually. So every 8 kilobytes or every 1 megabyte, you get a separate authentication tag. And then they do some stuff with the associated data to kind of tie those chunks together, so you can't rearrange them or duplicate them or anything like that. And so now when you're reading in data, you're reading in, say you're asking for like 500 bytes or something here, what it's actually going to do behind the scenes is going to read in an entire chunk, 1 megabyte say, buffer it itself internally, decrypt it, authenticate it, and only when it's actually verified is it going to pass it to your application. So this process method here is only ever getting verified plaintext that has been authenticated. Again, it just throws an IO exception if a tag fails, but it does that before it releases anything. So even if you just log that and ignore it, you've not processed anything that's been tampered with. So you're failing safe. You know, we talk about in security about failing open versus failing closed. So this is failing closed. You know, it's not releasing anything that it hasn't authenticated. So that was secret key encryption. There's also secret key message authentication codes that I won't go into because they're pretty similar to what I'm about to show you, which is signatures. So digital signatures, another classic example in cryptography. So you have a private key, you're going to use it to sign some data that you're then going to send somewhere, and then other people can use the public key to verify the authenticity of that data. So again, super easy in Tink, right? You just have your key set and you get this public key sign. So it's technically it's going to use the private key, but it's called public key because it's public key crypto. And then you just sign the data and you get back a signature. And then similarly to verify, you get a public key verify instance. So these are different. They're not just a generic signature class. And then you call verify. So a couple of things to notice about this. Firstly, getting the verify thing, this has to be done on a public key set that only contains public keys. If you've got private key material in there, that will actually throw an exception. And it's just to kind of safeguard against you accidentally sending your private keys to somebody else, you know. And so your code or your downstream code will fail if you've accidentally included private keys in there. And secondly, most signature APIs return a Boolean. You ask, is this valid or not? And it returns a Boolean, yes or no. But it's really easy to just not check that Boolean return value, right? The code will still compile if you don't check it. Even in code review, quite often you wouldn't notice that somebody is not checking the result of the verify. And so this is actually, it doesn't return anything, this API, and it throws an exception if it's not valid instead. So again, they're just making it harder to ignore failures. In languages like Go, which don't have exceptions, it returns an error value, and you have to check the error value. But in Go, there is compiler checks for making sure you're checking error values most of the time. So that's signatures. There's not really a huge amount to say about signatures. Public key encryption is a bit more complex. So I have to go into a little bit about how this works, unfortunately, for reasons that are hopefully clear. So most public key encryption is not pure public key encryption, and this may be known to many of you. But just for those that don't. So normally when we do public key encryption, we do what's called hybrid encryption. So a public key encryption scheme like RSA has two problems. One is that it's very slow compared to something like AES, typically orders of magnitude slower. And it's also, there's a limit to how much data you can encrypt, so typically a few hundred bytes. And so what we do is hybrid encryption. So we generate a random AES encryption key, say a shared secret, and we encrypt our message with AES, which is nice and fast, and then we just encrypt that random AES key with RSA. And then we send those two things along to Bob, and Bob uses his RSA private key to decrypt that unique AES key, and then uses that AES key to decrypt the rest of the message. That's how RSA encryption has worked for donkey's years. A modern twist on it is what's called the chem-dem paradigm. And this is kind of, it's been around for about 20 years, but it's only really becoming a thing now because of the looming threat of quantum computers. And so a chem is what's called a key encapsulation mechanism. And it's kind of like a generalization of that idea of RSA encryption. So you feed in, so Alice is here, she wants to send a message to Bob, she's got Bob's public key, she feeds it into a chem, and the chem is going to spit out a fresh random data encryption key, and also what's called an encapsulation of that key. So you can think of it as like the encrypted key. And then she uses her DEM, which is a data encapsulation, but it's really something like AES, to encrypt the rest of the message, and then she sends the encapsulated key and the ciphertext. So these are logically two arrows here, but they're typically one message. And then so Bob can then call his chem and say, okay, decapsulate that key with my private key, and he'll get back the same data encapsulation key, which he can then use to decrypt the message. And the reason for this change is that although the old RSA approach works for RSA, it works for pretty much nothing else that looks different to RSA. And in particular for what we call post-quantum encryption schemes, which are the replacements that are safe against quantum computers, they don't work anything like RSA encryption and decryption. But they do fit with this thing. So instead of your application generating an AES key and then asking the public key to encrypt it, you let the public key system generate it for you, and typically it derives it in some way. So there's a little bit of complication that you need to kind of understand for why things are the way they are. But mostly in Tink, this is all hidden for you again. So again, we have our public key set here. So this is Bob's public key, and we're going to get this hybrid encrypt. So that's why it's called hybrid encryption, because it's doing this thing. And behind the scenes, it's doing this chem-dem stuff. And then we just say we're going to encrypt it. And we give it our plain text and our associated data, and it's going to give us back a ciphertext. So an important difference here, so we said we used authenticated encryption for symmetric encryption. The security guarantees of public key encryption are different. It's not authenticated, but it is protected against tampering. So you protect against information disclosure and tampering, but you don't protect against spoofing, because anyone with the public key can produce a message. They can encrypt to anyone. And so you don't get that guarantee of where the message has come from. So that's hybrid encryption and public key encryption, and that's kind of covered all the bases, right, of how you're doing things. So you can see with Tink that there's a lot of complexity that's being hidden behind the scenes for you and being taken care of. So now we come to the bits, the more complicated bits. So there's a nice quote from Leah Kistner, who was at Google, I think, when she said this, which is that cryptography is a tool for turning lots of different problems into key management problems. And that is often the way with crypto, is that people learn about the algorithms and they implement their crypto in their code base, and then they, well, what do we do with the keys? Right, and so Tink doesn't do this. Tink doesn't just leave the key management for somebody else to worry about. It's a core part of the library, is key management. And if you notice from those code examples I was showing there, we weren't dealing with individual keys, we were dealing with what's called a key set, and that is a set of keys in Tink. And the reason why we're doing that is one of Tink's key design goals is to allow something called cryptographic agility. And that's basically the idea that the set of algorithms that we use to encrypt or decrypt or sign and so on, what we consider a secure algorithm changes over time. So, we used to think things like MD5 and RC4 were secure algorithms, and now those have got serious security vulnerabilities. So we want to be able to change the crypto algorithms we're using over time in a secure way. And Tink does this via these key sets. So one way you could do it, cryptographic agility, is what's called in-band negotiation of algorithms. So this is famously what JSON Web Tokens do. In JSON Web Tokens, you have a header on every message, and it has this algorithm field on it which tells you what algorithm was used to sign that JSON Web Token, or to encrypt it even. And the problem is that there's this algorithm called none, which means no security whatsoever. And so as an attacker, you can get a signed JOT. You've logged into a website, say, and somebody's using JWTs as their session tokens. You can get one of these, and you can say, okay, right, I'm going to change the payload to say, role admin or whatever, and I'm just going to rip the signature off and change the algorithm to none. And a surprisingly large number of websites and libraries just accepted that as a valid JOT, and it caused endless kind of security vulnerabilities. There's a website somebody set up, which is like how many days since the last none vulnerability. I think it has actually been probably over a year now since the last one, so we're doing well now. Another example of that attack against JOTs, so I'm going to pick on Jots a bit here, which is common in crypto talks, was what's an example of what's called a confused deputy attack, which is kind of very generic. But the idea is that somebody was signing stuff with RSA, and so they're using their private key to sign and public key to verify. But again, an attacker could change the algorithm to a symmetric signing algorithm, in this case HMAC, and then use the bytes of the public key to sign the Jot. So they can make changes and then take the public key, use the bytes as if it was a shared secret, and sign stuff. And again, loads of libraries just went, sure, fine, that works, because they weren't checking what algorithm was supposed to be used with that key. And so there's a principle that comes from Moxie Marlinspike, who's the co-author of the Signal Secure Messenger and Protocol. And he said, you know, if you have to perform any kind of operation on a message before you've authenticated it, then it will inevitably lead to doom. And this is called Moxie's cryptographic doom principle, which is a pretty cool name for a principle to have named after you. And so Tink tries to avoid this, right? So one way you could avoid it would be to just not allow cryptographic agility at all and just fix one set of algorithms forever, which is kind of what the NACL library does before. And there are some protocols and key formats and things like that where they do that, and they just fix one set of algorithms and they say, right, that's going to be secure. And if there's ever a problem with those, like the looming invention of quantum computers, well, we have to like stop the world and upgrade everyone to version 2 at the same time, right? And this goes against Google's own kind of software engineering principles, which they document in this book, one of which is that all software should be designed to deal with change over time. And so Tink is designed to allow cryptographic agility in a safe way. And it's something that I call key-driven cryptographic agility. It's not a standard term by any means, but the idea is rather than putting the algorithm that you used in the message, you put it in the metadata associated with the key. So that key should only ever be used for one algorithm. You should only ever use a cryptographic key for one purpose. And so you're storing your key somewhere securely, and so you store some metadata with it saying what algorithm it's for. And this is exactly what Tink does. So the algorithm is associated with a key, not with the message. And so this is what key sets do in Tink. So a key set, as the name implies, is just a set of keys that are going to be used for some purpose, like encrypting messages or signing messages or something. And each key set has a bunch of metadata associated with it, each key in the key set. And one of those fields it has is, I think it's actually called type rather than algorithm, but it tells you what algorithm that key is used for. And this accomplishes two things. First of all, it prevents these kind of attacks against Jots, because whenever you look up a key, you know exactly what algorithm it's going to be used for, and you don't look at the message at all. And secondly, it allows you to change the algorithm over time. So here we've got 3 keys that have been generated. These first 2 were using AES in Galois counter mode, and this last one is called using one of the Dan Bernstein's algorithms, which we call char poly generally, because that's a bit of a mouthful to say. And so the way this works then, when you think about when you're encrypting a message or signing a message, right, you're producing something new, there's a key which is referred to as the primary key, and that's the key you're going to use whenever you're producing something new. So if you say, I'm going to encrypt this message to Bob, it's going to say, right, what's the primary key in this key set? It's this one, so I'm going to use this algorithm to encrypt that. And so by setting your primary key in your key set, you're deciding which algorithm you use. So that's how you pick your algorithm. But when you're receiving a message, so you're decrypting something or verifying a signature, you can still use the old keys that are in there. And so this key ID is unique within the key set. And so when you read in a message, you look up which key ID, and that tells you which key, and then you look up the algorithm associated with that key. You don't try other algorithms. That key works with that algorithm. So this allows you to move nicely from using old algorithms to using new algorithms while still having a period where you're using both. And so this encourages those two kind of good practices. One is this cryptographic agility, and the other one is regular key rotation. It becomes, if you're using key sets everywhere in your code base, it becomes easy to rotate keys regularly. And as someone who's had to retrofit key rotation onto a code base that just use single keys everywhere, I can tell you this makes life a lot easier. And so to kind of support this, so when you encrypt something with Tink, right, it puts this kind of standard header on the front, or its own standard header. So it has this kind of key ID, and then when it's reading back in, it can tell which key you're using. There's also raw variants of the algorithm which don't include the key ID if you have to interoperate with people that don't understand these key IDs. In which case it will try every key in the key set, which is the sort of thing that worries people who don't know much about cryptography, but trust me, that's a perfectly fine thing to do. So the actual, how these key sets are managed, Tink takes a very opinionated view of this. So typically, if you're used to things like Java key stores, they're encrypted with a password. So when you create a key store, you create a password, and then it encrypts using that password. The problem with this is that what typically happens then is you're running some web server or something like that. You have your encrypted key store on the file system, and right next to it on the file system, you have an unencrypted file with the password in it, which is, you know, sometimes people do better than that, but often that's the case. And so if somebody has access to the key store, they probably also have access to the password as well. And so the Google Tink designers said, we're not going to support that at all. We're just going to force everyone to use what's called a key management system. So you can either have a totally unencrypted key file, and you can put it in your secrets management system or something like that, or you use a KMS. And they support, so most of the cloud services now have a key management service, and that's where you can store your master keys all securely, and they're probably backed by a FIPS-approved hardware security module and things like that. And so you load up your application, and it loads its encrypted key set from disk, and then it calls out to the KMS to decrypt that key set in memory. And it supports a bunch of them for cloud stuff, and then it also, as I said, it supports mobile development, so they have integrations with the Android key store and the iOS keychain. So you can use your nice hardware root of trust on those devices. So I made fun of JDOTs a few times. So JDOTs are kind of like this, they're a bit like those old style crypto libraries in that they provide loads of different options and things, and they're very easy to mess up. And I say that as someone who's involved in the standardization of JDOTs. So Tink not only provides those primitives, but they decided that JDOTs are so widely used now and so often screwed up that they provided support for them directly in the library in a way, again, that's kind of secure. So they have a bunch of APIs for kind of creating JDOTs. So first of all, you create this what's called a raw JOT with this builder, and you can set a bunch of stuff in it. And that raw JOT, you can't do anything with that. You can't convert it into an actual string JOT to send to anyone. All you can do is sign it. So in this case, we're using a MAC, so a symmetric message authentication code. And you only get the string back when you compute the MAC. So again, it's kind of steering you towards secure patterns. And likewise, in verifying, you only get this verified JOT. So this verified JOT is the only thing that allows you to actually access the claims in the JOT. You only can get one of those back from calling the verify method. So it's kind of interesting. Again, it's like their signature verification that through a signature, this time they're returning a specific type, and you only get that type back after verifying something. So in your code, you can pass around a verified JOT in all your stuff, and you know that whenever that gets called, it could only have come from having actually verified the signature. So this is kind of a nice pattern that they embody, which is called sort of, we often talk about secure by design in crypto and kind of shift left, and this is kind of secure by construction, right? There's no way the type system is enforcing that the only way you can access the content of the JOT is after you've verified the signature on it. So that's pretty good. I think we're a bit early. So that's kind of summary then. So Tink then is designed to be kind of easy to use and more importantly to be hard to misuse. And this is a kind of a theme of secure library and API development in the modern world, is that it's not enough to make things easy to use or to have one path that is easy to use. You've got to remove the easy to misuse bits as well. And likewise, I'd say I agree with the Tink developers that cryptographic agility is absolutely essential. We can't just assume that where we are now, all of the algorithms we're using are going to be secure forever. And there is the idea of quantum computers coming in the future. And so there's a bunch of features that I've pointed out, some of them in Tink as well, that make the code easy to audit. So for people like me who look at crypto code and secure code quite a lot of the time and review it, Tink is great because when you see these types being used in the code, you know exactly what you're getting for those things. And so it's really good. There's also some other bits I didn't show where it has some markers that you have to use when you're accessing like raw key material and things like that. So it's really nice to go into your IDE and you can just search for all uses of this class, and those are the bits that you really need to pay attention to. So that's kind of my rundown of Tink and its various features. So does anyone have any questions? I don't know if we have a mic, by the way, but yeah, anyone have any questions? Yes?
I was wondering, why do you think the older libraries were so much worse than what's out now?
Why were the older libraries so much worse than what's out now? So I think it's because we just didn't know any better back then, really. So cryptography was still kind of developing. You know, a lot of these libraries were designed in kind of like the 90s and early 2000s, where, you know, the main reference for cryptography was things like Bruce Schneier's Applied Cryptography book, which is, I like Bruce Schneier, but that book is really dated, and it's kind of like, loads of people still reference it now, but it's basically how to build an old-style library as a book. You know, it's like, here are 5,000 algorithms that you could implement. Aren't they cool? Yeah. And so, yeah, I think that was just a sign of the times that we just really didn't know. Like authenticated encryption, right? It wasn't really considered a thing until later. Any other questions? Okay, well, you get extra coffee time then. All right.